Hi everyone. This is just a real quick overview of the one-way analysis of variance, which we call Anova. Just go by the nickname. Just a little disclaimer. They're building a house right across in the lot across the street from us. So if you hear some pounding and cranes and so forth, that's you'll know what it is. Anyways, what we want to do is, in this video, I've got a total of 3 videos on Anova. In this video, I just want to introduce the concept and go through a little bit of the sort of what we're trying to accomplish here. So, first of all, when do you use Anova? That's one of the big questions we have in this course. Anova is used when you have quantitative data, so measurements of some sort, distances, lengths of time, so quantitative data, and you're trying to compare the means of 3 or more groups. All right, so we've already done tests when you've got 2 groups, but what if you have 3 or 4 or 5 groups or more even? Anova is designed for comparing the means of 3 or more groups. So for example, a classic example, and I think we have one in our text, is comparing the mean gas mileage for all 8-cylinder cars, all 6-cylinder cars, and all 4-cylinder cars. So that you're comparing the means of 3 groups, all 8-cylinder cars, 6-cylinder cars, and 4-cylinder cars. Now, so what are the possibilities there? So I'm going to get my pen going here, and I'll do it, say, I'll do it in blue today. All right, and let's make the thickness a little bit bigger than it is. Let's go up to about that. So we've got 3 groups we're comparing here for this 8, 6, and 4-cylinder cars. It could be that, and let's sort of think of the heights of these bars as the gas mileages. So this may be the gas mileage for the 4-cylinder, for the 6-cylinder, and for the 8-cylinder. It could be that the heights are all the same. In other words, the gas mileages are all about the same. Or it could be that, say, the 4-cylinder gets a whole lot better gas mileage, but the 6 and 8-cylinder have about the same gas mileage. That's another possibility. So 4 on average has more than 6 and more than 8. Could also be that the 4-cylinder gets really great gas mileage, 6-cylinder cars get pretty good gas mileage, but 8-cylinder cars are gas guzzlers, so they get pretty poor gas mileage. So it could be that we get a situation like this. Okay, now I'm going to switch colors here. Hold on a sec. And note that when the groups are all the same, when the averages, remember we're looking at averages, when the groups are all the same, that is your null hypothesis. Again, the skeptic would say, there's no difference. And you like that? There's no difference. When there is a difference, it doesn't mean necessarily that the groups are all different. That is possible. But it could be that just one of the groups is different than the others, the means. So HA, here are 2 possibilities for HA. So this would be an HA where one of the means is different than the others. This is one of the a possibility where for an HA where all of the means are different from each other. So to summarize that, what you've got is, for this situation, HO, the skeptic would say that the mean gas mileage, and let me get my pen going again, the mean gas mileage, because we're talking about means, for all cars, since it's an inference, in the 3 groups is the same. Symbolically, you could write that as that mu1 equals mu2 equals mu3. The alternative is at least one is different. So the mean gas mileage for all cars in at least, all right, one of the 3 groups is different than the others. So the alternative is written out in words. This is a hypothesis test. So the decision rule is reject H0 if the p-value is less than alpha, what's given. The test statistic is here, it's called an F ratio, and it's called the mean squared treatment over the mean squared error. Now I need to talk a little bit about what these things are. In general, the mean squared error is an estimate of the standard deviation of essentially the average of the standard deviations of all the groups together. Okay, so the spread, remember standard deviation is a measure of spread. So I take the spread of group 1 and the spread of group 2 and group 3 and however many, and I average those together. So the MSE is basically an average of the spreads, or standard deviation, of all the groups. The mean squared treatment is equal to essentially the standard deviation of the basically of the whole group, the group as a whole. So mean squared treatment is basically the standard deviation of the group as a whole. All right. So I want to look at the different possibilities for F, and so for that I'm going to bring up a different graph here. Let me go down and bring that graph up. Here it is. So this is a little program I've written, and I've got these three populations. So the black, the red, and the blue distributions all represent populations. So if the three groups are all the same, so they're never going to be exactly the same, but they're all about the same. So I've got there you go. So they're all about the same. Well, in that case, the average of the standard deviation of group 1 and the standard deviation of group 2 and the standard deviation of group 3, basically they're all going to be about the same value. All right? And they're all going to be about the same value. The total standard deviation, the standard deviation of the group as a whole, the spread of the group as a whole, is going to be about the same as well. So if the groups are all the same, then the standard deviation of each group is going to be about the same as the standard deviation of the whole group. So that would say your F ratio equals 1. Now, what if one of the groups is different than the other? So I'm going to move the two of the groups down a little bit lower, and one of the groups is significantly higher than the other one. Now, in that case, again, the standard deviation of each group doesn't change. Standard deviation, again, is essentially a measure of spread. So the black and the red, okay, and the blue also have about the same standard deviation. You would average those, you'd get the same value you would whether they're near each other or far apart from each other. But in this case, the standard deviation of the group as a whole, it's now spread out over a much greater distance. So when some of the groups are different, the F ratio gets a lot bigger. So to summarize that, okay, let me go to the next slide. If the H naught is true and the means are all relatively close, then your F ratio should be close to 1. If HA is true and some of the means are different than the others, then the test statistic is going to get a whole lot greater than 1. So that's what we're looking for. What is the F ratio? Is it close to 1? That would say probably the means are all the same. No reason to doubt we've not rejected the null hypothesis. There's no evidence that in that case that the means are different. If the F ratio is a lot bigger, and often you'll get 20 or 30 for an F ratio, then that would say, oh, okay, I think at least one of the means is bigger than the others. So you look at your F ratios. The p-value is a probability of obtaining that test statistic from the sample. So obtaining that whatever F ratio you had, if there truly is no difference. So if you get a very high difference, you shouldn't have that if the means are all the same. So you'd have a small probability. If the p-value is small, reject H naught. If the p-value is large, do not reject H naught.